Welcome to Machine Learning on the Edge. I'm Zach Shelby, co-founder and CEO of Edge Impulse. And on this show, we're talking about data and machine learning having a huge impact on all industries. The technology is really changing the way we think about data and how we engineer solutions. We're here at GTC 2024 live. Huge pleasure to welcome Sally Ward-Foxton.
Thank you. Thanks for having me on the show.
Sally covers AI for EE Times and an electrical engineer yourself.
Yes.
This is a huge moment for Nvidia, for artificial intelligence, for silicon as well. And we'll get into what this all means, right? Jensen's big keynote in a moment.
Yeah.
But first I wanted to talk about you.
Sure.
As another electrical engineer. What brought you down into the space of silicon and AI?
So in terms of career, I did my master's in electronic engineering, University of Cambridge, so always kind of was headed in that direction. But I've ended up where I am through several actual strokes of luck, as it happens, which is usually the way. I got my first job as a journalist right out of university, and from there basically kind of fell in love with writing about technology. Being a journalist is a really great job because it means you get to see all brand new technologies even before they hit the market, before everybody else. You get to find out the secrets, find out what's happening first, and I really love that. It's about talking to people and finding out about people, companies and strategy as well, and I really love that angle. But yeah, I've been a journalist for about 20 years, writing about electronics. That's my whole career. So when I joined EE Times 5-6 years ago, at first I was covering the whole of the industry, but after a while they gave me AI as a beat, and it was kind of early days for AI. At first I was like, what is this? What is this going to be? I didn't realize that one decision basically would make my whole career.
And now we have Jensen with 11,000 people at the SAP Center. I was like,
the amount of attention that Nvidia is getting and that GPUs and this technology is getting is absolutely astounding right now.
Let's talk about the Jensen keynote. My takeaway, not easily shocked, was like, wow, this is big, bigger, even bigger. And now we're transferring the entire world's internet communication capacity on a GPU backbone. I'm like,
yes, it's absolutely mind-blowing. So with the new Blackwell GPU, it's 2 die right next to each other in the package, so it's twice as big as Hopper, about 2.5 times the performance because they've gone to a new process node as well. So the GPU is one thing, super impressive, very, very cool, but also when you see the racks, that's where a lot of the performance uplift is going to come from. For these generative AI models, you need to communicate across multiple GPUs, they all need to talk to each other at the same time. So Nvidia's made really big strides in the switching in the racks and so on, and the networking and communication to really boost performance. I think so. Even if you get 2.5x from the new GPU, we're getting more like 25 or 30x performance uplift from the whole rack. So I can't understate how much this communication bottleneck has been holding things back.
It almost comes to mind like this is a kind of nation-state competition to afford one of these data centers now.
It's going to be expensive. We don't know the price yet, but we know it's going to be expensive. Jensen was on stage not that long ago talking about sovereign AI and how governments should be looking at AI and what they should be doing, using their own data with their own nuances in their culture and trying to build their own AIs, which I think is a really interesting point. Do you have to be a rich country to make a sovereign AI? I don't know right now, but I think we're going to start to see governments and countries building their own AIs for sure.
Now, as this all gets bigger and bigger, right? What does it mean for the edge industry, right? What's the possible trickle-down effect? I think of this like space and NASA, right? I've always been a space person, not because of space in particular. I think we should take care of nature here. It's my own philosophy. But I find pushing the limits of technology, right?
Yep.
And then transferring that to commercial applications. What Jensen's doing is kind of similar, right? This is pushing the limits of even physics to do Gen AI.
That's right. Even Formula One cars, that technology ends up in your own vehicle eventually. Which I think we're definitely going to see that effect on hardware the kind of architecture decisions they've been making on the big scale will come. Some of those things that, as appropriate, will come to Nvidia's smaller platforms like Jetson for the robotics and so on.
True.
Definitely, yes. I think there's also an angle on when we build these really huge, big AI supercomputers. That's how we do AI research today. That's how we train the biggest and the best models and state-of-the-art models. And the more advancements we can make in research kind of will trickle down as well to more efficient models that can run on smaller hardware and so on.
All right, so we might start to see new model architectures like transformers making their way more and more.
Or the next big thing, whatever that is going to be.
Post-transformer.
Somebody's going to invent something more efficient. We still don't know what's coming around the corner, but this research kind of drives the whole industry, and you need the supercomputers to do that.
I think it's a great way of thinking about the holy grail of generative AI data centers that Jensen is clearly driving with a vengeance, right? And
Absolutely, yeah.
Excited to see what happens at GTC next year.
Yeah, me too.
So let's talk about generative AI as an AI workload, right? A lot of talk here about LLMs and LLMs getting bigger, right? So the newest OpenAI ChatGPT model, 1.8 trillion parameters.
It's a lot, right?
That's like exponentially growing in the complexity ends. But at the same time, we have people talking now about small language models. Where are we going to see some of the first applications of these language models on real edge hardware, right? Disconnected from the internet?
So I don't think we're going to see it coming to microcontrollers necessarily just yet. I think first places you're going to see it are on the bigger end of the edge scale. So autonomous vehicles maybe have some processing power. Let's run an LLM so you can speak to your vehicle, access the features that your vehicle has, for example, and the car can kind of talk back to you while you're driving, I think is a really interesting use case. Anything that's a kiosk where you interact with it and it's kind of on the edge, it's edge compute. That will get an LLM that can speak to you kind of in real language and kind of help you in real language. Anything that does concierge services or anything where you're ordering products, even restaurant ordering, those kinds of kiosks and robots will get LLMs.
We recently had a elderly care case come our way that was interested in LLMs for emergency services, right?
Right.
What's the context of an emergency, right? Somebody's fallen down, okay, we can detect that. But what's the situation, right, that they're in? Is there someone else there that could possibly help? How can you interact in a way that you understand what's going on for emergency services if somebody can't speak? That was really interesting, right? Way of using video and LLMs at the same time.
So if you have these LLMs to kind of add context to other data as well, that could be a really interesting paradigm.
Exciting. We're excited to see where generative AI goes on the edge. Let's talk about acceleration.
Okay, my favorite topic.
Both of our favorite topics. Like, a lot has been going on in add-on acceleration, add-on boards, M2 boards that you're sticking into general purpose CPUs to do more and more acceleration. I'm not quite sure for what, where that side of the industry is going. We're going bigger and bigger. Our inference workloads on edge really getting that much larger. But then we have a lot of acceleration making its way into SoCs. Like, does this start to just become table stakes for any SoC maker that you have to have some math acceleration? Like, remember the days of cryptography?
Yes.
In IoT, right? I was involved with that, and it was like,
now it's got to be on the SoC, otherwise.
Yeah, there was a time where I was like, oh no, there's one special chip that has cryptography acceleration, and all of a sudden, everybody had it.
Yeah, you kind of have to have it. In terms of the M.2s that you're talking about, those are going to be around for a while because they're going into edge boxes and appliances where it's aggregating video feeds for a security camera or something. So it's a bigger installation. It's not edge, endpoint kind of edge.
Yeah.
At the endpoint, we are seeing separate, smaller accelerators with these novel architectures, which are super cool and super fun for me to write about. But
like
will they be
distributing the workload within the edge machine with like?
Yeah, so let's have an accelerator from BrainChip or Sentient or somebody where it's a separate chip and it's alongside your CPU or your microcontroller. I think eventually a lot of that will go down the same route that you're talking about for cryptography. It'll go onto the SoC. It'll be a block on the SoC. because that makes the most sense for embedded use cases where for power efficiency and integration and so on. I think we will get there eventually. Not today, but eventually.
Very interesting. We have a good example of what's happening in the industry now. This little box, this is just a AI-powered camera reference design that we helped build with a bunch of different partner and customer cases.
Okay.
One of those being nature conservation. So it turns out that a lot of endangered species, poaching, human conflict, nature conservation cases like elephants in Africa really can make use of computer vision with AI in the field. So deep in the forest, in the jungle, it needs to be left there for months at a time. Very hard to go collect data. This has no acceleration.
Okay.
So this is an STM32H7, so high-end Cortex-M7, a lot of external memory, so we can put models that range from 10 to 20 megabytes in size even into this. And with software techniques, right? Quantization, compression, re-architecting some of the ways that we do object detection, we can do fairly real-time object detection on this. And because it's a microcontroller architecture, we can do that for a year of battery life.
Okay.
With a certain number of PIR events per day where we capture images.
Okay.
And that's with no acceleration. So it's really interesting, like, as we get acceleration into these types of existing SoCs, right? Say the next generation of ST microcontrollers has an accelerator. Where's that going to get us and bring us, right? Like, what's the kind of optimization we should be thinking about from a device manufacturer's point of view? Like, all right, I've got a camera.
Yep.
We don't have acceleration. We're going to do a little bit of AI. Now we want to add acceleration for the next generation.
Yeah, I mean, if you're looking at reducing power, doing more efficient ML, you definitely need acceleration today. But I guess it's a balance of, can your application handle the extra cost that you're gonna face?
Yeah, so we certainly could burn through inference faster.
Yeah.
With an accelerator. That would allow us to go back to sleep faster.
Yeah.
So to improve our sleep duty cycle, right? Because low power modes in microcontrollers, we can go very low.
Yeah.
I could also see the need for always on. We talked about Sentient a little while ago.
Correct, yeah.
That's really innovative in the way that we can really run always on, say, instead of a passive infrared sensor, we could do something with like an audio detection. Maybe
sure.
If we heard an elephant.
Sure. Okay.
Rather than saw random movement, right?
Okay.
A lot of false images that way. I could see that always on capability being really interesting too.
Yeah, there are a lot of, there are several at least always on type of accelerators on the market. So picking the right one for you, I guess. A lot of those are in analog, which is very exciting too.
As well.
But yeah, it's an emerging market, let's say.
I want to talk more about these applications and industries, right? We touched on a few things like automotive. We're seeing the most forward-looking companies right now across medical devices, energy, manufacturing, logistics, and warehouses. We have a little warehouse application running behind us. They are adopting artificial intelligence into their edge systems, embedded products. But it's like the very early wave of adoption. Like, what's holding us back? Why doesn't all the industries just adopt this stuff much faster?
Yeah, it will take time. There are a number of things, I think, that are really coming together to kind of crash everything. I mean, software is always, the hardware is emerging and it's working, which is great, but software vendors, software stacks, I think some of those definitely, there's room for improvement. As those mature as well, things will get a little easier. Education, people are developing these kinds of products. They're not necessarily data scientists or ML engineers, and they're going to have to be, right? So there's a level of education required as well. There are also things for commercial deployments I think are not quite there yet. This kind of, to help you deploy at scale, how do you do that today with something that is an emerging technology? How do you handle product life cycle? How do you update in the field? All of these, some of these are bigger question marks than others, but there's still question marks right now. So yeah, as things are maturing, we're trying to sort out these problems, but I don't think we're quite there yet.
And something I agree with all that. In addition, like we're seeing a lot of problems with how do we get a hold of the data?
Right, yeah. Yeah. Where does it come from in the first place?
What is useful data, right? Like what kind of data can you apply to AI versus applying it to maybe a normal engineering process, right? That's code-based. So where does useful AI data come from? How much of it do you need? And then how do you get started? Get into a deployment and then use that deployment to collect more data. That's actually one of the more interesting paradigms I've been seeing lately is like this idea of an active learning loop.
Yeah.
Where don't try to spend half a year or a year making the world's largest data set of whatever, right? 1 million samples of this or that before you even try to deploy it in a real system, because it might not even work.
Yeah.
That's expensive, right? Building data sets. So why don't we start small? Put a small model there and then use that model to detect when you don't do something right? What are the things that you miss? Yeah. Let's take samples of that data, push that back into your data set, start auto-labeling and testing, right? Can we use that data to improve the accuracy of this model? Super interesting.
I think we're making strides on augmenting with synthetic data as well, right at the moment, which can help. But again, I think it's still developing. You know more about that than me.
Well, a lot of talk about Omniverse here at GTC. And we're finding that this kind of digital twin type of environment is very useful for synthetic data generation, especially in industrial environments where we're working with factories, for example, that haven't been built yet.
Sure.
Oil and gas facilities that are so remote, you would need to fly a helicopter to go collect data. That's expensive, right?
Right.
So really difficult environments, difficult to go measure in. So like this warehouse example behind us, that was built all with Omniverse. So that's entirely Omniverse modeled because the warehouses are actually really hard to go out to. They're far away, it's expensive to send a team to go collect data. So instead, one of our engineers was fed up of traveling to the warehouse, created an Omniverse model himself, and then we have a connector to just feed that data into a data set. So that entire data set is Omniverse generated. And then we can train a model and then deploy it back to the Omniverse model.
Yeah.
And test it in lots of different lighting conditions, angle conditions, kind of get a more robust model. I think there's a lot to this kind of like digital twin usage in synthetic data and like creating better models. Super interesting. Sally, thank you so much for
Thank you.
being
Thanks for having me on the show.
Thank you for joining us on Machine Learning on the Edge. Welcome you to our next episode, and please join us at GTC next year.